Okay, good afternoon. Welcome to this talk. It's great to have Kartic here. Kartic Subr is a faculty at Edinburgh. He is a Royal Society researcher. That's the title. But it's great to have him here. He was visiting earlier. He's a Bangalorean, so he keeps visiting many times. But the first time he visited IISc, he also gave a series of lectures as a part of the GYAN program that was well attended by students from all over the country. Now he's going to come here and talk to us about a wide variety of projects. I think there is some common theme there, that there is a combination of some physics-inspired MLAI and his interest in graphics and I think geometry and topology. We will see that as a part of the talk. So I think a little bit about Kartic. I think he is kind of hawked from across different continents and countries. Did his PhD at UC Irvine and then moved to Grenoble in France, and then has been at different universities in UK. Currently at Edinburgh. And today he's going to talk to us about a combination of vision, robotics, protein design, and simplicial complexes. And let's see what the connection is between all of them over here.
Thanks, Vijay. Yeah, so let's see which of those topics we can touch later on. But first, I'd like to motivate some of my work using this image. If you look at this picture, you see that on a daily, what can be seen as trivial problems, but are quite hard if you think about the physics underlying them. So if you think about things like dough and sand, all of these, specifying the physics underlying these materials is quite challenging. But we're able to learn this from a very young age. So it's not like we need sophisticated learning methods. So what are we doing as humans, on the cognitive side, to be able to understanding what the physics is? So that's something I started to think about. And I think that I came to these two sort of controversial, mainly one controversial sort of thread that I could analyze, which is, a lot of approximation theory focuses on accuracy. And yes, we always strive to get approximations that are very accurate. But what if I flip this and I said, I don't care about accuracy. Give me something that runs really fast. Is there any use to this? And I found that in different domains, as I posed this question, people came back and said, yes, we would love to have something like that. So one of the sort of the central themes of what I'll be talking about today is this idea of, can we sacrifice accuracy for speed? And if we want to do this in a principled way, then how difficult is this problem? So even though the domains might be different, I think that the idea is, once you've committed yourself to a sort of a theoretically known approximation algorithm, then you suffer from many different assumptions. So you might assume that your boundary conditions are all realistic, but in the real world, there's no spherical cover. And similarly, you want efficiency, but imprecise input. So if you think about an automated driver, a car going on the road, all of its measurements come from very noisy measurement devices. And then if you try to solve a Navier-Stokes equation, providing those as boundary conditions, then you get, usually you get a very unstable system. So these are some of the reasons why choosing an approximate method is usually valuable in the real world. And the question is, of course, then how do you design your approximation? So my group looks at timely approximations. This is going to be the topic of my talk today. My name is Kartic, as Vijay said. I'm a Royal Society University Research Fellow and an Associate Professor at Informatics. Before I touch upon all this, I'd like to, I'm not sure how many of you know about Edinburgh. Has anyone known or been? Okay, good. You're better than me when I applied. So my wife actually got the position at the department first. So when we went for her interview, we didn't know where it was. Even though we were living in the UK, we had to Google it and drive there. So, and then they told us, oh, actually we are ranked pretty highly in the Times and so on. For us, it was news because we'd never heard of this. the department, but it's exciting research going on there. So we have about 150 to 200 academic staff. We have a massive robotics lab with equipment that's worth close to about 20 million pounds, I think. We have the Center for Robotics, then that's the big department where I sit. So it's a very exciting place. If you're ever in the UK for a conference, let me know. This is my group. I have about 5 and 1 other PhD student who just joined, who's not on it. And what we try to do is look at approximate physics, like I showed you on the first slide, and try to use a bit of machine learning in combination with the approximate physics. And then try to apply it to different domains. So Alex here works on topology. Leo here works on proteins. Bruce works on the physics side. Ola works on the genomics side. And Sean also works on the physics side. I saw that some of, I'm not sure if any of them's here, but I looked through the faculty pages and I saw, and I thought, some people do work that is relevant to the type of stuff that I do. I'm not sure if anyone's here. So I'm going to break down today's talk in terms of 3 different sort of layers. Of course, we're all interested in the theoretical analysis, because if I just come and tell you I came up with this approximation and I don't analyze it, then you don't know if it's useful to you. You don't know how you can trade it off for whatever your domain needs. So it's important that whatever is developed needs to have a solid theoretical base to it, with which you can analyze it, but also understand how to tweak. Then there's the pre-computation approach, which is quite common. If you have a hard problem, then one approach is to look at the problem, pre-compute some of the data, and then try to use that in finally solving the problem. And of course, there's learning, which today you can't escape. So regardless of what you do, it seems like if you don't have that cherry on your cake, it's not going to sell. But I'll show that this is more than just that. And I'll give you different examples from different domains. So for the learning, I'll show you some problems in robotics. But to understand problems in this domain generally, is this visible from the back? Yeah, can you see? So if you look generally, when people propose approximations, they look at time on the x-axis, error on the y-axis. And what you want is that your method gets more accurate as you run it for longer. Right? So this convergence plot is typically what we see. And if you have a very accurate method, typically it converges over time to something that's very low. Whereas if you take an approximate method, for example, here to measure wind speed, you might have very quick results initially, but then you don't actually get accurate over time. So it's hard to make those methods accurate. And if you ask people what method they prefer, it would be hard to give you an answer just looking at this, right? Because if I only had a time budget here of 1 and I wanted an answer, actually method A gives me a more accurate answer. So this raises the question, should I use A, B, or C? And there's no one answer, it depends on the application. So that's sort of the central idea behind this whole analysis, is to pick an application and understand, given a time budget, how can we design an approximation that works for that application? So for example, here, if you look at the initial motivating example, and I say, I want to take one of these robots, and I want them to pour a liquid. Again, if we come back and try to solve this with Navier-Stokes equations, it's not really going to be feasible. A, you need to be solving these equations in real time as the robot pours to be able to predict where the liquid's going to fall. B, your containers that you have might not be sensed properly by your depth channel, and then you have all these noisy boundary conditions, and your solution might not even converge. Those are some problems with this. Of course, latency is the biggest problem. So what we did was, in work with a PhD student, Tatiana, what she did was she had this hypothesis that I can take a really stupid physics engine. For example, a video game, if you've played video games, you can run in liquids and it splashes. So her idea was, let me take that video game physics engine and see if I can use it to solve this problem. Obviously, when people design fluid simulations for video games, they have the time budget of 1,000th of a second. That's how much time you can afford on the physics. So they don't spend time making sure it's accurate. And so one of the biggest challenges here was how do we take this physics method that is so inaccurate and make it to do something useful. The general idea here, I won't go through the details, was to set up two parallel universes. In one universe, you had whatever was happening in the real world. So for example, this robot was picking up the liquid and pouring. And in the parallel universe, we tried to mirror that in simulation. So this, because our video game engine was able to do this at high speed, we would track things like the stirrer, for example, and then mimic that in the simulation model. And then we would see how much they disagreed on some prediction. And we call that discrepancy. And then we tuned it so that so in this particular paper, we took a Bayesian approach, but you could take any learning approach for that. And we sort of ran a Bayesian optimization to maximize the likelihood of the estimates of the parameters. So for example, one of the reasons this was necessary was, let's say a robot wants to pour oil instead of water. Now the video game engine, physics engine, doesn't have a notion of viscosity or other parameters of oil. All it has is some variables that the programmer hacked in and said, x equals k, k1 equals 5. And so what this step was doing was trying to find a mapping that made sense for that particular physics simulator. And that's where the learning component comes. And said, oh, when it's oil, then set k1 equals 6, k2 equals 7, and so on. It wasn't so explicit, but you get the idea. So that's what this optimization did. Now, once we have that, we could then predict, once we fit that, then we could predict. So you can change the container, you could change the settings, and just run the simulation. And if the simulation gave you an answer of 1, you would know how much to offset it by and how much the spillage would be. So very coarsely speaking, what we did was we took one step, where we learned the parameters of the liquid, and then we moved to the second step, where we could pour based on whatever we had learned to see if the robot had learned anything useful. Any questions on this? Yeah.
So I suppose you sort of learned the best fit model that explains the real time.
That's what we did, yeah. So we sort of, if you look at this theta, yeah, we learned thetas that best fit, but the theta doesn't necessarily need to be only for the parameters of the liquid. It could also be things like geometry. So if you change the container, you might run a different simulation. Yeah.
So how did you actually, after you learned the model, how do you plan for an optimal form?
Yes, so the plan for the optimal, what we did was we just used roles, we unrolled the simulation and then minimized. So we just did a minimization of whatever goal was. So in this case, the goal was we want to minimize the spillage. So we unrolled several iterations of sort of pouring, and we found the action policy that resulted in the lowest spillage. So we were actually learning the policy in this step. So in the first step, we learned parameters. In the second step, we learned the policy. That makes sense? Any other questions? And we found that this sort of idea was useful for a variety of robotics applications. So for example, here, we used a drone trying to sense where there was a leaky liquid fluid. So we had a carbon dioxide cylinder, we had a nozzle, and it was kind of leaking out of that nozzle. And our goal was we would release the drone somewhere on the field, and the goal was to sort of track out where the cylinder was. And the way people typically did this before was they would send the drone out and have measurement points. So the drone is equipped with a sensor for carbon dioxide. And what they would do is they would measure the carbon dioxide every few meters, and then they would have a big chart. They would take it into the lab, and then they would look at the distribution, and they would say, oh, okay, this is where we predict the sources. The problem with that, obviously, is two things. One, while you take measurements, the wind speed is changing direction. The wind speed is changing, the wind direction is changing. And two, obviously, by the time you've taken this to your lab and processed it, maybe everything has changed. All the conditions have changed, and when you go back, the parameters are different. So one of the key goals here was to discover a path. And the idea was, use the sensor to perform what is called active learning. And so as you can see here, the idea, again, like in the previous case, was we have some likelihood there of where the source is, and every data point that we take, we update that and predict where the next waypoint should be. So this would happen dynamically. We would just release the drone. And one of the big challenges in Edinburgh, for those of you who have been, is that it's a very noisy environment. So the wind is very strong, and it keeps changing directions. It's not steady wind. There are lots of models that work when you have steady wind conditions, but when your wind direction keeps changing, it is quite a hard problem. So what we had here was we had some kind of approximate physics calculation going on for wind direction, trying to hypothesize what wind direction would have caused this. We had a sort of very cheap wind sensor on the drone, and that would tell us the wind. But obviously, if you can, as you can imagine, the drone has propellers, so that affects the wind measurements and so on. So that was one project, again, where we used approximate physics to perform a task that is actually non-trivial to some extent. And then we had another example of this approximate physics idea, where the idea was that the robot, we would throw a ball from this side, and we wouldn't tell the robot which ball we are throwing. And the goal for the robot was to intercept the ball. And obviously, if you know all the coefficients of restitution and you know all of the initial velocity, you would imagine this is a trivial problem, right? You can just plan. But in this case, we don't know what the table is made of. We don't know what the ball is made of, any of this. What it has a chance to observe is how it bounces there. So that we have, because the camera is looking at it all the time. So in real time, what we were trying to do is try to understand, but model the physics here. So we would have some coarse approximation for the physics model. And as we saw it bounce here, we would use that model to fit what parameters the ball likely had, what performance, what parameters the table likely had. So again, it's all similar in terms of the course idea, but it's different for different applications. And then we would move, obviously, then there's the control part of the robot, the arm which needs to move. In this case, the control part is trivial, it just moves in one plane. Well, we extended this by putting a little black cloth here so the camera couldn't see beyond. So the camera would see up to where it crosses this, and then we would have a black cloth, and the robot would still be able to plan, because almost all of the information they needed from the physics came from just that part of the trajectory. Again, that's why the coarse models are helpful, because we can work with very low latency, very low amount of data, and so on. This is another example. This is still work in progress. We're having trouble moving this to the clinical side, but we've done the tests in a lab environment where we had a little box of gel, and we put something in there which we imagine is a tumor. So we had some object in there, and we equipped the robot arm with an ultrasound scanner. And the goal here was for the robot. So if you've ever been to a doctor and seen how they scan, they usually move the scanner till they find a position where they think the image looks good. And that is not really well defined. There's no scientific formalization of how that should be done. So what we did was we took samples from a doctor. We asked the doctors to come in, several of them, perform scans. And this in the robotics community is what's called learning by demonstration. And what we tried to do then was to learn a policy that would then act like a human physician would. So then once the policy was trained, we put the block in front and asked the robot to autonomously move to the position where it could see the tumor best. And obviously there are different ways to validate this. And when we validated it, we found that it was able to get to about 95% fidelity of the tumor pose as a human trained physician would. And we showed that this was much better than if you just had a human who wasn't trained in this. So if you or I went and tried to scan this, we would perform far worse than the algorithm itself. I'll take a little water break. Anybody has any questions on any of this?
So for the second bit, what extent was the physics, you have to look at physics, or you would just simple vision-based approach?
So we did take a vision-based approach. So this was before transformers, so we had the looped network. So we did use a neural network in this case, but the physics model was just the base model based on which we drove the dynamics. So we had some information of physics. It was not just a neural network looking at the video and predicting. It was, so the balls were extracted and then some dynamics of the balls were provided to simplify it. Now, of course, you might be able to do it with just visual input, but the question is how much data do you need to train it? Right. So in this case, we were just looking at one bounce. So we didn't have a big corpus of many balls bouncing, which is your typical Google style, right? So they do it in that fashion, and there are many papers that do it. But the key here was when you have sparsity of data, when you don't have this massive corpus, what do you do?
So I guess my question is this a demonstration that can learn the control when there is physics involved in your processes, or was this? I mean, for this specific application, I'm guessing that you can just have a simple tracker, ball tracker at real time, which.
No, oh, I see your question. No, that doesn't work because the latency in moving your arm is quite poor. It's quite poor, yeah. So if you tell the robot when the ball is here to move here, you won't be able to do that because it moves a bit slow. I mean, yeah. So for non-robotics people, most of these robots move very slowly, except the drone. Everything else moves super slowly. That's a good question.
So how is this different from the previous slide? Are you also learning to fit the difference between a dynamics model and what you observe?
Yes, except in the previous slide, we used explicitly a simulator. Here, we don't use a simulator. We just because in this case, the equations are much simpler than for a liquid. We baked understanding of just simple Newtonian laws. And it was much easier than running a full-fledged simulator in real time. So perhaps, and one of our goals was this, if you have these balls made of deformable objects, then maybe you'll need some FEM and stuff, and then it may become a bit harder to solve. But because we knew we had fairly rigid objects bouncing, we didn't need the full simulation framework. So that was one difference. The second difference was we used a neural network rather than just the Bayesian approach. So we tried to show that you can, one of the criticisms of our previous work was, oh, you used a Bayesian approach, this is going to be not scalable and so on. So here, because we use a network, we can show scalability, and we can show that even though we use a network, we don't need lots of data.
So the network helps you optimize it.
Yeah. So the network helps us optimize the parameters, but not in an explicit way. So it's formulated as a learning problem, but.
Does the network also help to generalize also?
Yes. So that's why we are able to, as a parameter, not worry about whether it's a tennis ball or a table tennis ball, because that kind of is part of the fitting process where it learns the parameter. And it does it explicitly. So unlike in the previous case where we explicitly learn parameters, here it doesn't implicitly learn parameters. There's just a mapping from observations here to your policy. Good. Any other questions? Are there any roboticists here? No? Then I can get it. Yeah, so that was, again, in all of these problems, the general trend was, coming back to this graph, was to take an approximate method and try to learn how much or how far you are away from the real solution. You can think of it in a way where you take a really stupid physics model and you teach it with experience that if your prediction is here, you must actually be predicting here. So that's one way to think of it. And that's where the learning comes in. In the first case, it was learning parameters, and this was the space of error in the parameters. But in the second case, it was directly modeled on measuring where the source was, so the error was where the source was. It doesn't matter what this error is, but you can think of it generally as using a cheap simulator to learn complicated physics. If you have a very stupid method here, then you need a more sophisticated learning method. So there's a trade-off between these two is what I was trying to illustrate with different examples. And that's what I'm trying to push now in my ongoing research, which I'll briefly touch upon. But the general method, as you see, is that question? So the general method, as you see, is you somehow guess these parameters, whether it's viscosity, restitution. You run some simulation and then you find a loss and you keep cycling through this. But And then, in my background, when I did computer graphics, there were different types of simulations. So we did, liquids, but we also did light, sound, things like fracture with FEM and so on. The problem is most of these simulation methods, if you want to be accurate, they use Monte Carlo, and Monte Carlo is very slow. So the question is then, what do you do if you need to run realistic simulation situations like this where the physics is not easy? You can't afford to do, as I said, full simulations of these. So there's a big trend in what's called differentiable physics. Anyone here works on differentiable physics? No? Where instead of trying to do this, if you build a simulator that can be automatically differentiated, then with respect to the input parameters, then you could avoid this part and then update your parameters by doing the backward pass through the differentiable sequence. Anyway, the details are not important unless you want to work on it. But what I can tell you is this has been very, very popular as a research area over the past few years. So if you haven't heard of it, I would say Google it up and you'll find some really, really interesting results of how you can build a differentiable simulator and how you can use it for very interesting applications. And interestingly, when I looked it up, when I searched for publications with the topic differentiable simulation versus title, it gave very different results. So if you want to work on this, put it in your title. It's my takeaway. Anyway, so coming back to what we were looking at, if we can build a differentiable simulation here, then we can avoid a lot of the problems we had previously.
Question.
Yeah.
There's always a question that if your models that you use are very cheap, very inaccurate, they probably entirely miss up. You learned a very good policy, very transparent.
Yeah, so that is always true. So the question is, if you are able to pour, so in this case, what we measured was how much liquid do you spit. And for that task, it did well. But it doesn't mean that if I take this and ask that same learning method to run on the drone to predict where the leak happens, it will work. So that's part of the issue here is that unless you have a coherent simulator, you can't generalize. So the idea of I guess one of the key words in your question was transfer. So the transfer learning component of it is non-trivial. However, that is true even if you use the same simulator, because unless it is also going to be fluids, maybe you have to get a different, so you need an FEM simulation instead of a SPH simulation. And then anyway, you will be having a different simulation framework. You can't use the same. But what I'm trying to say here is the general principle of using a simulation based on which you learn is now fairly common, but at the time when we did this, it wasn't that common. And partly why I'm setting this up is this was all past work, but there's, if you want to do this sort of idea where things are differentiable and so on, those of you who are familiar with neural networks will automatically see how you can set the simulator up as a neural network. So over the pandemic, when, as I was telling some of you, my students were busy with their projects and taking care of themselves, I thought I'll do my own pet project. So this is my own project. And I didn't really know much about neural networks before this. So I thought I'll start bottom up to try and see if I can learn it myself. So one of the first things I noticed was, for those of you who don't know neural networks, anybody here is an expert in neural networks? Nobody? Oh, okay. Good, I can say anything I want. So the idea is you have different nodes, and then you have different inputs. So in this case, each node has a function of 3 variables, and then you combine them somehow and you get your final function. That's the one layer simplest neural network for you. But then I had a question about, if I use a neural network to represent this function, how can I compute its integral? Right? So I was interested in calculating the integral of f just using the weights here. Because a lot of people have trained neural networks to approximate a function. But then if you want to get the integral of the function, you don't really have a way to do this. The way you have to do this is go back and train to learn the integral of the function. So what I was trying to do here was to come up with an analytical method that so once you train this function, take the weights of each of these layers and then learn what the integral was. So I calculate the integral directly from the weights. I won't go into the details of this paper, but what it was useful for doing was this parameter estimation. And so I showed you earlier we took a Bayesian approach to do parameter estimation, and here we sort of took a learn from data example. So imagine that you have something here. So this is a scene, you've simulated light. So this whole thing is a computer graphics render. There's light bouncing around, and you're interested in what is the amount of light that comes to this part of the scene. Now there are two parameters here. One is what is the material of the bull, and the other is what is the angle at which the bull is. So if I turn the bull, given one θ1 and θ2, I will get this image, right, of the turned one. And if I move in that, then the bull is turned. If I move back, the bull is here. If I move up, the bull's material has become a bit rougher, and so on. So those are the two parameters in play here. And as you can imagine, depending on what my choice of parameters are, what I observe on the right wall will be different. Right? So for example, if I'm here and I look at the right wall, I see some noisy pattern. And one of the questions I was interested in was, if I can only observe this, can I guess what orientation the bull was? It sounds like quite a hard problem, because there's so many possibilities. Plus there's Monte Carlo simulation, so there's noise, there's two different parameters. And there are lots of methods that do this. So if you look at computer vision, this is what the base is, right? You want to observe an image and try to predict something. But what I was interested in doing was slightly different. I wanted uncertainties. And that's not something that you can get easily. So what I was interested in was, instead of a point in the space, I wanted to observe this image and get some notion of what is the distribution in my parameter space. And this turned out to be a harder problem. Again, I won't go through too many of these details, but if there's any graphics people interested, we'll come back to this. But that network and the integral that I talked about earlier was an easy way to frame this, and then there was an iterative Bayes rule application based on which you can infer. So what this shows is, if you look at the really light gray curves, they show you initial estimate distributions, and the dark gray is what happens when it converges. Now let's look at θ1. As that gives you a rotation angle, this is the reference, and you can see that the distribution converges to around the reference. For roughness, it doesn't really. It kind of gives you a mode there, but not really converges to a nice tight distribution. So what this tells you is that even though you might estimate the parameter correctly around 0.06 for roughness, that your uncertainty is very large. And again, the difference between this method and what we looked at before is that here we are having some notion of uncertainties around the physics, which we also did earlier, but now we have it because we observed data beforehand. So in the case where you have lots of data and you can train, this method is useful. And if any of you have come across nerves, then this is basically what they have. They have lots of data, they've trained it. And then if you want to go from there to making any statements about parameters with uncertainties, it's unclear if you can do that. Any questions on this bit?
Is it synthesizing?
Yes, so it's synthesizing novel views. So if you haven't looked at this paper, it was a revolutionary paper in 2020. You can go and look at it. What they did there was they took some pictures, and then they were able to synthesize many other views from there without. Any computer graphics people here? Nobody. So maybe I should skip this part.
Partial graphics.
Partial, yeah, I know, Vijay, but I'm not sure. But anyway, I'll just tell you briefly. So this is probably a hardcore maths paper, so I won't go into the details, but I'll give you an idea of what I was trying to do. And this pertains to the bottom layer in that pyramid, where I said you need to do some theoretical analysis. So what we did here was we looked at how light reflects. There's models for it. So for example, this equation is an integral equation. Like a differential equation, it has an integral operator. And if you solve that equation for L, that means you can understand how much light there is everywhere in the scene, and then you know everything. So just let's not discuss the equation. It's a well-known equation for about 35, 40 years. It has been simplified into a simple representation in terms of operators. And this is the emission, and this is the light we want to know. it doesn't matter now anymore what I'm trying to solve. So if you think from a maths perspective, what we have is we have some space. You can take a single point, L is a function in that space, so it's a functional representation of the space. And this operator is a linear operator, which applies to the space, and it changes L to TL, right? That's pretty much what happens when light bounces in the scene. So if light comes off there, it hits this, let's say, surface. There's a linear operator that defines how the light is then scattered. So there's the emission, there's the linear T operator that you need, and then so this equation characterizes all of that. So we did some theoretical analysis of it, and because nobody here really cares about this topic, I won't tell you specifically what it means, but what we showed was something about the compactness of this operator. And we showed actually that the operator is not compact, which means any approximation that you do cannot be bounded. I mean, the error for any approximation cannot be bounded uniformly. So this was a pretty big statement, because that's trying to say that in the last 40 years of approximation, that operator, nobody has ever got a uniformly convergent solution. And then when you have such a problem, which is so hard, there are two questions to ask. One, if you're using light to measure scattering in a tumor and you want to detect, say, tumor detection, then you may care about solving this precisely. So you may want to try and see how it matters that it's not common. Two, if you're doing this to generate pretty pictures, as I did when I was at Disney Research or other places, for animation, then why bother with any of this stuff at all, right? So there's two different approaches, and it's a bit like the complexity discussion we were having after lunch. If you know a problem is in NP hard, then you just carry on with an approximate algorithm. Like, you know, there's really no effort in trying to find a polynomial time algorithm, but then the question is just about, can I do it in n to the whatever 2.5 as the approximation of 2.56? So in that sense, I think this is a quite a significant theoretical result, and then we use this to show on the stuff. Okay, in summary, what this is basically we have all the theory, right, and we have really practical methods, and how do you bridge these two? And that's sort of the goal of most of my research, is to try to use either pre-computational machine learning as the bridge. And they work in different ways, and they have different advantages, and it depends on which domain you're in. But that's sort of important. The problem with both of these is that they don't generalize. As your question was very relevant, can you transfer these skills from one to the other? That you can only do with a theoretical understanding of whatever the physics is for that particular application. So in this case, we did it for light. We're working on something for fluids and protein dynamics and so on. So the general question is, yes, I'm happy to do this theory, but I want to know how this theory is going to affect this bridge. That's really what my research is about. I think that's about 45 minutes. I have a few slides on some other stuff, but I'm not sure if I should. Are you happy to listen to more, or do you have questions? Yeah, happy? Okay. So there's some work. I think some of you mentioned that you're interested in topology, so I included these couple of slides. So this, for those of you who are not familiar with topology, the problem is, let's say you're given some object like that, and you're given 3 different loops here on this particular problem in topology. If you look, they're all cycles, but they have different properties. So for example, you can imagine if this is a piece of string and you slit it on the surface, that you might reduce it to this blue one if it was an elastic string. Whereas this one will just collapse on itself. It has different properties. So they're all cycles, but they have different topological information. And the question we asked in this paper was, given some data points, can you find the distance of each of those points to the closest cycle? So the optimal cycle, closest optimal cycle. And again, I'll discuss the details with those of you who are really interested in this. But what we found was, a very simple theoretical property, understanding a very simple theoretical property of, the Laplacians on this complex. And typically what people do when they do approximation, whether it's PCA, SVT, whatever, is they take an eigendecomposition of whatever matrix you have, and then they take the top eigenvalues and say this approximates, it's a low rank approximate. The problem with that approximation for topology is all the interesting topological information is in the null space. So it's in the bottom 3 or 4 eigenvalues, in this case 2. So if you do any kind of diffusion or anything with a Laplacian or the eigen approximation of a Laplacian, you end up with something that gives you really no topological information. So the key insight in this paper was to flip it. Instead of looking at an eigen decomposition of a Laplacian, was to look at the decomposition of a pseudo inverse of the Laplacian. Because then if you take the top eigenvalues, they correspond to the null space. Anyway, for those of you who are not topologists, the takeaway here is you take, what we used here was a simple graph-based graph neural network. And we didn't do anything complicated with the neural network or the training or any of that. But what we did was we replaced the way in which weight aggregation or diffusion happens within a GNN when it's trained. Instead of training it with the Laplacian, we trained it with the pseudo-inverse of the Laplacian. And there was a little bit of engineering there. But then what happens is that you can feed it a complex, and then you can query the network for the weight at any node, and that's what we visualized here. So the color tells you how close or far, blue is close and red is far, to the nearest optimal cycle. And what the neural network was able to spit out is this information because of how the diffusion accounts for topology. So again, an example of using learning for simplification without much change to the learning side, but with insight on the maths of how this happens. Another work that some of you might be interested in, we chatted over lunch, was in approximation of domains. So far, we talked about approximation of physical processes, but sometimes the domain is important. So here we have a very fine mesh. You probably can't even see the triangles on the mesh. And you might have, say, a fluid simulation or some FEM or some other physics methodology applied on that. And we might want to replace it with coarse geometry. You want to coarsen your domain so that your simulation can run faster. Now, obviously, when you want to do that, it's not obvious what points to throw away in your original mesh. And there's a long history of approximate methods for domain simplification and so on, but none of them really accounts for topology. And one important part of this, so if you think of, everybody knows the Fourier transform. You take a signal, project it on the eigen decomposition of the derivative operator, which is sines and cosines, and you get some band, right? But what happens in higher dimensions? What derivative operator do you take? Usually people take the Laplacian. So what they do is, this is like a Fourier spectrum, but the domain is the spectrum of the Laplacian, which is the eigenspace of the Laplacian. And you say, give me this part of the eigenspace of it. It's a bit like doing band pass with Fourier signals. But now we're dealing with high dimensional domains. I've shown you a triangle mesh, but it could be a tetrahedral mesh inside. So what we showed here was that when people do this, the only algorithms we have to run these things is a 0th dimension approximation of the Laplacian. So the Laplacian is defined with respect to the vertices. So you can do a finite difference based on vertices or whatever filter you want. But what happens if you do it with higher dimensional Laplacian? So you can have a Laplacian defined over edges, over triangles, over tetrahedra, and so on. And we found that depending on what method you use to do these bandpass filters, you get very different results. So what we kind of came up with this in this paper was a general methodology for taking a model, coarsening it, and then run your simulation or whatever you want, and then project it back, lift it back into the original space. And the key in this paper was this coarsening. How do you specify what you want to preserve when you do the coarsening? And the interesting thing here is this is a part of an engine, and you can see that this part has lots of holes in it. So if you don't take care to retain topology, all those holes are going to be lost. So in this case, we would specify we want to preserve this band of the eigenspace. So we know that the low, the low eigenvalues, the vectors, eigenvectors corresponding to the low eigenvalues of the Laplacian keep topology. So we give it as one of the input considerations to coarsen while preserving that part of the eigenspace, that green shaded area that I showed. And because of that, then when you run your simulation, it's still high fidelity because it takes into account all the holes in the engine. So that was a paper which we recently put on archive. It's under review right now. But I think that's very interesting because now we can define coarsening based on any Laplacian. You can give it an n-dimensional Hodge Laplacian and say preserve this band in the 5th dimension, this band in the 2nd dimension, and so on. And our algorithm is a very simple algorithm that runs very fast to produce the simplification. You can even think, as some of you were doing, topological analysis, it may be interesting now to take this, run persistence on this instead of this, and then see whether you get the same, bottleneck. You can look at bottleneck distance between them and so on. And we did some tests like that. We compared to Goody, and we find that Goody and most of these things are optimized to preserve only the L0 cycles, L1 cycles, whereas we can ask it to preserve arbitrary homology. Okay, again, I can stop now, but if you're interested in more diverse stuff, I can keep going. How many of you have a time constraint? No? You have to leave? Okay, no problem. Do you have any questions before you leave? No.
Thank you.
Yeah. So this, again, this whole idea of approximate physics, which I started with robotics, did some work with light and so on. I realized that there's some, again, during the pandemic, I realized there's some really exciting problems out there. So for those of you who are not familiar, this is a protein. We all have proteins in our body. And when I started this project, all I knew was I looked at my food and saw the protein there and I ate it, right? But then it's amazing that these proteins, what happens is when they go in our body, they get broken up, they get recombined into these amazing things that do work. And they do work by by doing what robots do. So they actually move, pick up things. So they, for example, they may tap oxygen, go there, release it. So very dynamic creatures. And we don't really think of proteins as being dynamic, but if they stop doing their dynamics, then all life would end. Right? So they're the fundamental basis for life in many ways. And the ways that proteins are described is just as a chain of identifiers. So every 3-letter symbol here identifies one amino acid or a building block of a protein. And what happens is, given this, you can represent it as a chain of different colors. And depending on the colors they have, they end up in some 3-dimensional shape. Right? That's the protein folding problem. Everybody knows that predicting this structure from this, knowing what the elements of the protein are, is NP hard. So we don't have polynomial time to do this. AlphaFold was in the news. Everybody has heard of AlphaFold because they solved this age-old problem. They came up with a neural network that would compute this folded structure given this string. And they were able to do this with pretty high accuracy. Right? And ultimately, when it's finished, it looks something like this. So each of those is one amino acid, and they settle in some 3-dimensional structure. So there's a competition every year on protein folding, and AlphaFold in 2018 came up with a method that worked really well, and they became famous. And then they came up with AlphaFold 2, which was even better. And again, I won't go into the details of how AlphaFold works, but I'm happy to chat about it. But essentially, what this meant was people consider this problem almost solved. Now, the problem with all of this and what I have is AlphaFold, of course, has solved a very interesting problem and a very challenging problem, but they don't market it in its true form, right? No protein ever has one structure. The whole point of the protein is that it moves and does things. So if you come up with a method that predicts structure from your string, you've only caught that protein in one pose, which means you can't say anything about the dynamics of the protein. And that's something they leave out in most of their marketing material, right? So what they actually want is not to go from this string to one pose, but we want to go from this string to some simulation, some specification that we can use to then run dynamics on this. And that is still a very, very open problem. But the good news is after AlphaFold, there have been other methods that allow you to then generate lots of this.
So that initial configuration often helps running the dynamics, because a lot of the dynamics is based on their homologies, so not the policy homology.
Yeah.
But so similar structures. Right?
Yes. So the problem is running dynamics, so for example, if you were to run, say, 1 picosecond of dynamics of the protein, then simulating that takes about 24 hours on a big, large-scale supercomputer. And so if you give it one position and you ask now span out the space, and if you're looking at, say, 10, 15 nanoseconds, you're still looking at enormous amounts of computation. Right. So what this has definitely solved is the structure problem, but what I'm trying to say is there are very open problems that are not solved yet. Right, so if you can somehow, and this is one of the things that got me into this, and why this is connected to approximate physics, is that my point is, if you can approximately predict the structure, as AlphaFold does, why can you not approximately predict the dynamics? Right? So that's the new space that I have PhD students trying to work on. But there's another interesting problem here, which is the inverse problem. So if I give you the 3D structure, can you tell me what string I should start it with? And this is actually a more realistic problem. So if you take, say, binding of, I don't know, COVID virus and its spike protein, often you know what 3D shape you want. The biologists have scanned it and they'll tell you, I want some protein that's in this shape. They very rarely will tell you, make me a protein with this sequence. Right? So the inverse problem, again, is not solved. So the question of, for those of you who don't know about inverse problems, you have light, you have a shadow here, these two shadows look the same, and it's not clear really what that object could be, but it could be a different object casting the same shadow. So the inverse problem is generally ill-posed. And what we have here is an inverse problem where we have some shape, we want to get this sequence, there will be multiple sequences that give you the same shape. And so that's a pretty hard problem to solve. And you can't do this brute force, even if you have AlphaFold, because if you have a protein of length 200 and you have 20 amino acids, your search space is 20 to the 200. It's enormous. There's more atoms than in the universe. So you can't really go through this using brute force. You need something clever. And I think this is one classic example of a very hard problem where maybe machine learning is useful. And that's sort of the first problem that I got into in this space was this design problem of given a shape, can you come up with, and if you remember, it's similar to the inverse problem that we looked at before, where we looked at the wall, looked at the green color, and tried to predict what the parameters were. Anyway, I won't go through the details. This is, in case there were protein engineers in the room, I thought I'd go through some details.
So there's no chemistry involved here at all, is it? Is it still about learning the physics?
Yeah, exactly. So this part of it has no physics because it's all static. So what we started with was the static part, and then we found that the static part itself was a pretty challenging problem. So this student, Leo, isn't working on the physics, but I have another student now who's starting to look at the dynamics part. But we wanted to get into the domain with first trying to take a simple problem, which was, so in this case, all we did was we found out if we had brute force training on a network, can we solve the problem? So you can think of it as the first step of showing why we need something more clever. And what we found was,
I guess my question was but does it stop at only the physics, or do you have kind of an abstract representation of the chemistry that goes in?
Yes.
And
yes, we do.
They often talk about these substructures.
Polarity substructures. Yeah. Yes, so we do have that. So what we showed was that if you just look at pure learning of signals, then you can do somewhat okay. You can still do better than the physics-based methods, but you can't really do really well. So right now what we've done is that we have a paper under review where the chemist has an input. So things like polarity, charges, and properties like that. And when they paint those, so in addition to this, if they say, I want this to be hydrophobic, this to be negatively charged, exactly what we're working on now. Right, so that's the chemistry side of things, but that still doesn't have physics. What the other student is looking at is instead of giving this structure, if you say, I want this structure to move like this. So let's say you give it keyframes of 5 different structures, and you say, find me the best sequence that will produce a protein that works like this. That's where we are. And what we found actually was all the machine learning work in this area was using this as a training data set, where the distribution across the different types of proteins were very skewed. So your machine learning algorithm would just get away by predicting anything as a 3-layered sandwich, and then you're fine, because I've seen so many 3-layered sandwiches that it's likely to be. So what we showed that if you want to use these kind of database methods, data-driven methods, that you need to normalize across all of this. And of course, that's well known in the machine learning community, but it wasn't in practice in the protein design community. So this is our paper, which does pretty well. I won't sell the paper here. And then we evaluate it using AlphaFold. So we have some shape, we design it, and then we run AlphaFold on ours. We find the shape that it gets, and then we find the error. And we found that we were able to design very close to the error. Again, I won't go through all of the graphs, but this is what it looks like. So the blue is ours, the red is the target structure. So somebody told us, I want a protein that is shaped like this. And then our method said, well, if you want that, then the first component needs to be leucine, the second one glycine, and all these different acids. And then once we put all of those together and run a simulation or ran it through AlphaFold, we got back the blue structures, which are fairly close. So again, remember, this is the inverse problem to what AlphaFold solves. And what we're working on now is the dynamics. So this is just a static view, but let me quickly skip through. That's what a protein looks like in our body, by the way. For those of you who haven't seen it, this is amazing. The first time I saw this, I just floored. So it's pretty much like a robot. So this particular protein called kinesin is transporting something across in our body. And as you can see, each of these things, right, it sort of creates a bond, breaks it, it moves. So as you can see, if that dynamics wasn't part of the protein, then it wouldn't be able to perform its function. It would just be like hair or nail, which are static proteins. So there's a huge amount of open problems in this, and that's what I'm excited by right now, is to take the idea of approximate physics with machine learning, and then see if we can produce simple approximate predictions for this, and then run them through the complex as using them as starting points. Again, this is one where in our blood, hemoglobin attracts oxygen, so there's a oxygen binding inside, and what happens is when it goes into the lung, it releases the oxygen. So examples of two important proteins in our body that perform dynamics. The enzymes that perform digestion are similar. Yeah, so basically I think we need to start thinking of them as machines, not as static structures. So there's a lot of scope if you do this, and there's scope in terms of all of the stuff that I said. So on the physics side, right now, if you run a molecular dynamics or a quantum simulation, you could be stuck there for months to get dynamics for one of those. If you look on the learning side, just doing everything data-driven is not going to work. There's just too much. You will need too much data for these kinds of dynamics. So obviously you need to make in physics. And as we saw with the other physics examples, they're complicated equations. So you can't just say, I'm going to come down the dynamics model. That's not feasible. So there are questions around all of these, which suggests that you need some approximate physics along with some learning mechanisms to model any of these. And the protein design and the dynamics community have been working on this for a long time, but they don't have the approximate methods. So there's some opportunities in the UK. So if you're interested after my talk, we can talk about them, whether you're faculty here or whether you're looking for a postdoc. I can show you venues where you can write grants to move to the UK. There's a lot of funding at the postdoc level. For the PhD level, as I was saying, it's not that much funding for international students. If you're interested in this, meet me after the talk, or you can send me an email. So coming back, I think there are lots of problems that we solve very easily. And I think across lots of disciplines, the core idea of how do you approximate physics to make something work is an interesting problem. So with that, I'm going to end if you have any questions.
Thank you.
No problem. So it's okay. We can chat out.
A lot of the so this is that drone. You showed that
Yeah.
Kind of searching for that gas leak. What if it's going in the opposite direction?
If what is going, the wind.
The drone is going.
Yeah. So if the drone goes in the opposite direction, your next reading will be low because it has the carbon dioxide sensor. So when you feed it into your model, it will tell you that it will confirm your hypothesis, or it may change your hypothesis. So let's say you assume initial hypothesis was that the leak is there. You went to the next point and you found that you have a lower value. Then when you update your hypothesis, it tells you that logically it should be behind you, right? Or depending on your measurements, where your next step. So you change your policy and then move towards.
I was about to ask, so when you had this figure about the error and the time available to run your, let's say, physics. So is there any underlying assumptions that you make about the error? So in terms of continuity. So for example, you also talked about topology, where if I want to introduce a notion of error, this is more discrete. We are talking about a discrete object. Error would also be integral. May not even have those benefits of continuity if you set up a error function. Forget about differentiable properties.
But hopefully it's monotonous. I think that's important.
Right.
So if your simulation produces error that's not monotonic, then it's very hard because you don't know whether you're reducing or increasing error. But it doesn't matter if it's discontinuous but decreasing, or if it's discrete, it doesn't matter. What you care about is at that point in time, is my error lower or higher? So I think monotonicity is a bigger question than this.
Right.
And some of these errors are integral. So even in the light example, the error was an integral over the patch. And that patch is not a point sample, right? It's a continuous area. You're integrating error, not only over the patch, but also over directions. So yeah, the error can easily be an integral, but it's important that it decreases. So if Monte Carlo was not converging, that would be a bigger problem. And that's the problem we have with
the protein. That is
no. So with the protein, the energy landscape is not monotonic, but that doesn't matter because we're not trying to minimize anything. We're trying to minimize energy, but we're not looking at error in the landscape sense. So you want to get to the global minimum, which is a challenge. Most often you get stuck in the local.
Since the protein is actually it executes dynamics.
Yeah.
So can you think of it as a dynamical system that you want to learn?
That's what we're doing now. So in fact, the current project we're doing, we're trying to replace it with a mass spring system. Just to learn to see how approximate can you be, and to then use that as a seed for the quantum or molecular dynamics. So you run your mass spring and it tells you this is the dynamics, and then you feed it to the molecular dynamics engine to see how far off we were. It's a bit like what we did with the video game engine. Instead of taking a video game engine, we're taking a different one.
But I'm a bit integrated. I mean, like a system which is constantly moving, like a dynamical system. For a protein, it's not static, yes, but there are a few configurations that are quote unquote functional, and the protein is able to go from one configuration to the other in order to do the execution. So, for example, in that that kinase example, the few configurations where it binds with the current setup and where it releases, so those are two different configurations, and it has. So isn't it sufficient to learn those specific
so in fact
configurations?
So in fact when we start now, the database that gives you all the dynamics only gives you those snapshots. We don't actually have the full dynamics. So when we look at a protein dynamics data set, it will give us
only those
snapshots of when they measured it. And we have to work out what parameters, like we did earlier, this beta, will generate a mass spring system that has minimum energy at those. And of course, then there's the environmental actuation and so on. And in fact, a lot of the molecular dynamics simulations, that's what they do. But they just do it at a precision that's much higher. And now they found that that is still not enough. You need to do quantum level stuff. And then when you do that, then simulation becomes even slower. So the question is now to again flip it and say, if I did it really approximately, and got all these dynamics positions and then ran it at the quantum, So if I can get keyframes, so again, going on. A protein, you can go onto the internet, it's like 3D printing. If you tell it, I want a protein with lysine, leucine, glucine, blah, 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 they'll just ship it and send it to you. That's not the problem. But the question is, if I want this dynamics, what should I have the sequence to be? That's the question. And that's not easy even if you have a quantum simulation. The forward problem is what the simulation solves. If you give it a sequence, the simulation will tell you what happens. But if I tell it I want it to do this, the inverse problem is not solved by the simulator. Yeah.
The video to parameter, the neural network that was correcting the trajectory, was it learning online, or was it trained on balls first?
No, so it was learning online. It was tuning online. So it was trained with some different balls, but we were not exactly using the same balls that it was trained on. So it was tuning whatever base model that it had.
So it looks at a little bit after the balls and then it corrected there.
Corrected there. Okay, cool. Thanks.
Given something from CSA.
Oh, come on, Vijay. It's not required. Thank you.
It's just a summary.
Thank you. Thanks.